Well met, my friends. This is part 2 to lesson 3.7, in which we are using something called free body diagrams to solve. First, a quick recap on what free body diagrams are and how you set them up. You probably don't need to write this part down, but please listen carefully. So step 1 in solving problems with this method is to label all forces. So in order to do this, you need to know all the forces that are possible in this class, and you need to know what direction they point. So here's a quick list. There is applied force, there is air resistance, there is normal force, there is kinetic friction force, there is static friction. I believe that's all of them for our class. If I come up with anyone, I'll add them to this list. Let me just look at it for another moment. No, that's about it. That's about it. All right, so those are the forces. You should go through this list and ask yourself, is this present? Is this present? Is this present? Step 2, after you label all the forces with arrows, you should write your net force equations. Once again, you probably don't need to write these 3 steps down, but it's a good idea if you've got the time. Write the net force equations. Many people have trouble with this because they don't realize that the net force equations are different for every single problem. They depend on the scenario. Is it a block that's sliding? Is it a block at rest? What is going on? So the important thing to remember, which we didn't write it this way yesterday, so this would probably be good to write somewhere. The sum of your x forces is anything that points right, rightward forces, I'll write it down here, rightward forces minus leftward forces. So anything that's left is negative, anything that's right is positive. Then sigma Fy will be upward forces minus downward forces. So the equations will differ depending on the forces that you label up here. And now that I think of it, I'm forgetting the most common force, which is gravitation. Gravitational force, which always points down in our problems. And finally, step 3 when you're solving these problems is to plug in many equations. Yesterday we wrote this as make substitutions. It'll be good to have these all in one place. You probably have them in yesterday's notes, but here they are again in case you forgot them. Sigma Fx can be replaced with MAX, so that's one mini equation. Sigma Fy can be replaced with MAY. There's your second mini equation. We also have the very familiar Fg equals Mg. What else? We have Fk equals mu Kfn. We could also, I'll put a dotted line around this one because you have to be careful with it. So static friction, depending on the context of the problem, we might be looking at regular old Fs, or we might be looking at Fs max. So I'm going to put a dotted line around this one because you have to be careful with it. You can't always just plug it in. So I'll provide specific examples about that if it becomes relevant. Otherwise, we'll ignore it. Today we won't use it at all. So there are your steps. You need to have this organized somewhere in your notes, or just memorize. A lot of people can just remember the steps. There will be problems. If we were doing this in person, I would have problems where I grade your ability to label the forces with arrows. Haven't figured out how to do that on a computer yet, so we might not be graded on our ability to label the forces. However, you need to label the forces in order to write the net force equation, so it all ties together. So, onto the official stuff, onto the mandatory stuff that I need you to write. We're going to do 3 or 4 examples here. I think we'll have time for all 4. Some of them are quite short. So I wrote them in a bit of a hurry, so I'll read them aloud in case you have trouble seeing what I'm writing. Here's our first example. A 70-kilogram crate is pushed to the right with an applied force of 900 newtons. Calculate the acceleration of the crate if the coefficient of kinetic friction is 0.45. A 70-kilogram crate is pushed to the right with an applied force of 900 newtons. Calculate the acceleration of the crate if the coefficient of kinetic friction is 0.45. Maybe take a moment to pause and digest what it means. I'll also talk about what it means right now. So here's what we have. There's a crate. This is the mass of the crate. So that is M in the equations. It's being pushed rightward with an applied force of 900. So that implies that our applied force points to the right, and also the crate is going to move to the right. We're going to calculate A, lowercase a, acceleration of the crate. And think about what direction is that? Is that a y? Is that our vertical acceleration? Where's our horizontal acceleration? It's actually going to be horizontal. So we want to calculate the acceleration of the crate. This is ax because the crate is moving sideways. They want us to know what's the sideways acceleration because the vertical acceleration of the crate is going to be 0. And they also gave us the roughness. The coefficient of kinetic friction is 0.45. No unit for that. So let's go through our steps. Step 1 is label all forces. And you should kind of go through a questioning process here. Is there an applied force? Is there an air resistance force? Is there normal force? Let's go through each of those. Is there an applied force? Yes, they said directly. Applied force points right with a force of 900. So FA is to the right. Is there air resistance? No, it's not moving fast enough, and it's too heavy to experience a lot of air resistance. Is there normal force? Of course there is. It's on a surface. We can assume it's on the ground. So Fn points up. Is there kinetic friction? Absolutely. This thing is sliding on the ground. Therefore, kinetic friction is present. Anytime it's sliding, there's kinetic friction. Is there static friction? No, we just labeled kinetic friction. Can't have both static and kinetic. And finally, is there gravitation? Of course there is. Gravity is down. And that's all the forces on my list. I know that I'm ready to move on to step 2. So step 2 is write the net force equations. We want to write net force equations. We'll take any rightward force and subtract it by the leftward force. Take any upward force and subtract it by the downward force. In this case, we have all 4 of those things. So let's write the net force equations. This is step 2 in solving these problems. Sigma Fx equals Fa minus Fk. You can kind of see the XY axis here. Look at that. It looks like in math class we have the X axis and the Y axis. Here's your positive value, FA. Here's your negative value, FK. And same with the Y axis. There's your positive value. There's your negative value. So let's represent that over here. Sigma Fy equals Fn minus Fg. Bam. I am done with step 2. I have written my net force equations. Step 3, plug in your mini equations. So we'll take any, you kind of just look at the letter on the left of the equal sign. Find Fx and replace it with Max. Find Fy, replace it with May. Find Fg, replace it with Mg. Find Fk, replace it with mu k Fn. Now, so I would say this step is not tough, but you need to be patient. If you make mistakes, it'll slow you down. So, sigma Fx. I look at my list, I see Max. Fa. I look on my list for Fa, and there is nothing there for Fa, so I leave it as it is. Fk. I look on my list for Fk. Eureka, I've found it. Mu k Fn. And we'll move on to the other equation, plugging in from there. I'm going to make a little bit of a barrier here because it gets a little messy. Sigma Fy, I look at my list. I see that it is May. Fn, I look at my list. I see there's nothing there, so I leave it as Fn. Fg, I look at my list, and I see that Fg is Mg. Now, you may notice something here. Yeah, I'll hold off for a second on that. So, we are finished with the steps. We've labeled all the forces. We've written the net force equations, and we've plugged in the mini equations. So what we need to do now is solve it. Now we've got it set so we can solve it without much thought. So let's see what we're trying to do. 70 kilogram crate, okay, that's gonna go for M. Let's push to the right with a force of 900. Here it is, look at this. Calculate acceleration. But remember, we have 2 accelerations. Like I said before, they're asking us for AX. They're asking us for AX. So let's use, that means we're going to use this equation to get our final answer. Let's try to solve it. I'm going to start over here because when you plug in numbers, this is going to get much wider. The equation is going to get wider. So maybe I should have written it with more space. Anyway, so M, I will plug in M, 70. AX is what I'm trying to calculate, so I'll leave it there. Equals, okay, I plug in AX. FA, I'll plug in 900. 900. Let's put in parentheses. What comes after FA? It's mu k. What's my roughness? What's my coefficient? There it is, 0.45. Minus 0.45, and I reach an impasse. I've plugged in M, I've left A as it is. I've plugged in FA as 900, mu k is 0.45, but I don't have a number for Fn. And I can't solve for AX until we plug in a number for this. I can't just leave Fn there. So we find this equation right here. This is what will be used to calculate Fn. The thing is, it's actually a lot simpler than this. This is one of those cases where Fn is the same as Fg, and that's because Ay is 0. Think about it. We've got a crate going sideways. The crate is moving sideways, so what's the vertical acceleration of it? What's the vertical acceleration of this pen here? It's not going up and down. The vertical acceleration of this pen is 0 because it's not moving vertically at all. So in one swoop, I can kind of simplify this equation. M times 0 is 0. So I'm left with this. It just shows that Fn equals mg. So really, if you are comfortable with this, if you understand that normal force and gravity are balancing one another out, that they're equal, you could skip all this garbage. But it's good to set it up. I might grade you on your ability to set that up later on, so please go through the motions and set it up anyway. Here's Fn. It's just 70 times 9.8. You could even write in here 70 times 9.8. I'm going to do that. I'm going to save myself a step on my calculator. So really, we could have skipped all that. If you just remember that Fn, you know what, I'm going to write that on my mini list. Fn is sometimes mg. Sometimes. So add that to your mini equation list, wherever you keep that, and it'll be easy to solve things. Okay, so we're definitely not going to get through all four problems. Anyway, let's simplify this. So I'm going to leave the left-hand side 70ax, but I can type this whole thing in my calculator at once. It'll be 900 minus 0.45 times 70 times 9.8. It's important to have a calculator where you can type everything in before hitting enter. If you use an iPhone calculator for this, you'll get the wrong answer. The calculator does order of operations here before subtracting. It'll multiply these three numbers before subtracting. So I'm getting 591.3. 900 minus, I'm going to do it again, 0.45 times 70 times 9.8. Yep, 591.3. Divide both sides by 70. We'll have an answer. So our acceleration is 8.45 metros por segundo a la dos. That's the acceleration of the crate. So really, all we used was this equation. This one is kind of redundant. But still, going through this process is nice and mindless. You don't have to really think much about what's occurring in the problem. I mean, you don't have to be creative. It would be hard to just conjure this up out of nowhere without following those steps. Very advanced physicists can do that really well. Let me take a look at which problems here are the most important to go over. Yes, this one here. All right, we'll have time for the last two. I'm gonna skip I'm gonna skip the second one that I planned. Here we go. A girl squeezes the brakes on her bike pedal or her bike. Yeah, a girl squeezes the brakes on her bike so that she skids and slows at a rate of negative 5.23 meters per second squared. Calculate mu k if she and her bike have a combined mass of 80 kilograms. I'll read that again. A girl squeezes the brakes on her bike so that she skids and slows at a rate of negative 5.23 meters per second squared. Calculate mu k if she and her bike have a combined mass of 80 kilograms. Okay. So in this problem, the system, the thing that is experiencing forces is the combination of her and her bike. So it's her and the bike together. We want to know all the forces acting on them. She and her bike are putting forces on one another, but we'll look at them as one. What are the steps? Label all the forces. I'm going to go backwards through this list. Is there gravitational force on the bike and the gal? Yes, pal. Gravity's down. Is there static friction? No. They are in motion, so there's actually kinetic friction. I'll just say she slides to the right. I'll try to make that more clear on tests. So if she slides to the right, friction pushes left by definition. You need to know that. You need to know that friction is always the opposite direction of motion. Going backwards on my list, is there normal force? Yes, sir. The ground is pushing up on her and the bike, otherwise she'd sink down. And finally, there's no air resistance. So finally, is there an applied force? The answer is no. And that tricks people. She's moving to the right. So why is there no applied force? And it's because of Newton's first law, baby. An object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So she is moving right. She will continue moving right at that constant velocity. But this force is unbalanced. It will slow her down. So when you are pedaling your bike, you're sort of providing an applied force for yourself to keep yourself from decelerating. Here, though, the friction is pushing left. It is unbalanced and it is slowing her down. So there's nothing to keep her from moving forward. That's just inertia. She's just that's the property of inertia. Things keep going forward. You can only speed them up or slow them down with an unbalanced force. Anyway, I'm ranting. Let's do step 2. Basically, I want to reiterate there. All I'm trying to say is, for something to move forward, for something to continue moving, you don't need any force to let it continue moving. You only need force to speed things up or slow them down. I think that's the perfect way to put it. You only need force to speed things up or slow them down. Otherwise, they'll continue as they are. Okay, step 2, write the net force equations. Let's do it. Sigma Fx. Sigma Fx is our rightward force minus our leftward force. Well, that'll be nothing minus Fk. So it's basically 0 minus Fk, because there's nothing over here, which is just negative Fk. Sigma Fy, the net force equation is defined by any upward force minus any downward force. The only forces we have are Fn and Fg in the vertical dimension. Fg is negative because it's down. All right. Next up, well, that's it. That's step 2. Step 3, plug in the many equations. All right, from left to right. Sigma Fx, I look at my list, I see that it is Max. Fk, I look at my list, I see that it is mu k Fn. Sigma Fy, I look at my list, I see that it is May. Fn, I look at my list, I see that it is Fn. Fg, I look at my list, I see that it is Mg. Okay. What do we, well, okay, hold on. We're done with the 3 steps. We plugged in the many equations, we're good. Here we go. calculate mu k. Now we have to actually read the problem again, figure out what we're doing. Calculate mu k. All right, we're trying to calculate mu k. What about these other 4 letters? These other 3 letters, that is, M, A, F, N. Well, M, mass, is 80. AX is 5.23. And Fn, well, this is one of those cases where Fn is mg. She has no vertical acceleration. She's sliding sideways. She's not bouncing up. She's not going off a ramp. So Fn and Fg are equalizing. So we kind of don't really need this equation once again. I could just plug in mg right here. So this will, Fn can be mg as long as there's nothing pulling up, nothing additional pulling up or pulling down, or you're not in an elevator. So let's do it. Here we go. 80, AX is negative 5.23 equals negative mu k. You can go through this equation and solve for Fn if you want. You just have to remember that AY is 0 since she's not vertically accelerating. But I know that gravity's pulling down, Fn is pushing up. They are locked. They are balanced. So I know that actually Fn is just going to be 80 times 9.8. We won't always skip this equation. Sometimes it's very important. Sometimes this is the one we solve. I know to solve for this one because they're asking for mu k. So this one doesn't have mu k. Anyway, we'll solve here. Notice there's 2 negatives, so they're going to cancel one of that out probably. 80 times 5.23. You know what? I'm going to save myself some time here. Add JK. Why do I keep lying? Why the heck you lying? Okay. Let's do that again. 80 times 5.23. Always check your work. 80 times 9.8. 784. All right. We'll divide both sides by 784. 418.4 divided by 784. We're actually dividing both sides by negative 784. But I can already see that the negatives are going to cancel. Mu k is 0.534. If you get a negative mu k, you know you did something wrong. You probably just forgot to cancel out the negative. This is always positive, just like your attitude should be. Mu k is always positive. Okay. Last one. This one's going to be super easy, actually. Might have to streamline it. Here we go. Let's do this rapid fire. Don't even, write it down real quick. Book pressed against wall by 33 Newton force. Calculate normal force acting on the book. A book is pressed against a wall by an applied force of 33 newtons. Calculate the normal force acting on the book. So here's what that looks like. Is there gravity? Yeah, it's down. Remember, the book is being pushed this way. I'll say it's pushed to the right. Pushed right. So the applied force will be right. Go ahead and do this. Push this again. Push something against your wall. Think about it for a moment. Push so FA goes against the wall. What about normal force? Normal force pushes out of the surface. Up here, we were talking about the ground. This person's sliding on the ground, so normal force pushes out of the ground. It makes a 90-degree angle with the ground. Look at that 90-degree angle there. Normal force points this way. The ground is flat. But now we have the wall. The wall. The book is being pressed against the wall, so normal force has to make a 90-degree angle with the wall. That's pretty much all I wanted to show you in this problem. There's Fn. Static friction is the thing that keeps it from sliding down. And there's only one thing we really need to look at. We're going to kind of run out of time on this one. My video is already at 30 minutes. I know you only get 40. So here's the deal. This is the only one we really need to look at. MAX FA minus FN. This is one of those cases where FN is not equal to FG. FN is equal to FG when they are opposite, when they balance each other out. But here, have a look. We're going to have a 0 acceleration. AX is 0 because the book is not moving this way. AY is also 0. It's not moving that way. This is 33. You can kind of see the answer right there. Fn is just 33. So the point is, all I wanted to show you in this is Fn is not always up. And Fn is always going to be some sort of balance. So in this case, it balances Fa. So this one kind of goes beyond the 3 steps. So try to focus on the 3 steps. Try to do these. All right, I'll stop it here. Thanks for watching. I'll talk to y'all soon.